everyone, welcome to Let Me Engineer You. On this entry, we will have our comprehensive lecture on well hydraulics under PC5 groundwater flow modeling. Today, we will be diving into the mathematical principles that govern groundwater flow, the methods used for aquifer testing, and the critical mechanisms of contaminant transport and remediation. Let's get started. Next slide. Introduction to groundwater flow. In groundwater hydraulics, analyzing the movement of subsurface water is essential for sustainable resource management. When a pump is turned on, water begins to move radially toward the well from all directions. This creates a symmetric, funnel-like shape in the water table known as the cone of depression. Because of this natural symmetry around the wellbore, mathematical models of well flow are much easier to express using polar coordinates, specifically r, theta, and z, rather than standard xy grids. This simplifies complex three-dimensional flow into a manageable, mathematically elegant framework. Next slide. Equations of flow in polar coordinates. Let's look at the governing equation. For a homogeneous, isotropic aquifer, meaning the soil properties are uniform in all directions, the partial differential equation for radial flow is expressed as follows. The partial derivative with respect to r of the quantity r times the partial derivative of h with respect to r plus the partial derivative with respect to z of the partial derivative of h with respect to z equals the storage coefficient s divided by transmissivity t multiplied by the partial derivative of h with respect to time, t. Let's break down those variables. H represents the hydraulic head or water level. R is the radial distance from the pumping well. S is the storage coefficient. And T is the transmissivity of the aquifer. A key assumption we often make is that for fully penetrating wells in a perfectly horizontal aquifer, the vertical flow derivatives, the z components in our equation, are negligible and can be safely ignored. Next slide. Okay, let's have a sample problem for confined aquifer. When pumping continues for a long enough time, the system reaches equilibrium. This is known as steady flow. For a confined aquifer, which is sandwiched between impermeable layers, we use Thiem's equation. It states that the pumping rate, Q, equals 2 times pi times transmissivity, T, multiplied by the quantity, H sub 0 minus H sub W. All divided by the natural logarithm of R divided by R sub W. In this equation, Q is the pumping rate. H sub 0 is the original, undisturbed head. H sub W is the head at the well. R is the radius of influence, and R sub W is the radius of the well itself. In our first sample problem, city engineers use this exact equation to determine the maximum pumping capacity of a new municipal well without exceeding a safe 10-meter drawdown. By plugging the given transmissivity and radius limits into Thiem's equation, they calculate a safe pumping rate of approximately 3,873 cubic meters per day. Next slide. Now let's have a sample problem for unconfined aquifer. For an unconfined aquifer, where the water table is free to rise and fall, the math changes. As water is pumped, the saturated thickness of the aquifer actively decreases. Because of this, we use the Dupuit equation. The formula is Q equals pi times hydraulic conductivity, K, multiplied by the quantity, H sub 0 squared minus H sub W squared. All divided by the natural logarithm of R over R sub W. Notice the squared terms. These are crucial because they mathematically account for the dropping water table and the resulting nonlinear flow. In our agricultural sample problem, a farmer uses this relationship to estimate that his unconfined well is extracting about 2,000 cubic meters per day, based purely on the observed drop in his water levels. Next slide. Unsteady flow to a well. But what happens right after you turn the pump on, before equilibrium is reached? This dynamic period is called unsteady or transient flow. For confined aquifers, transient drawdown is calculated using the famous Theis equation from 1935. It calculates drawdown, S, as a function of distance, R, and time, T. The formula is drawdown, S, equals Q over 4 pi T, multiplied by the well function, W of U. To find W of u, we first must calculate the dimensionless parameter u, which equals r squared times s divided by 4tt. Once u is calculated, we look up the corresponding well function value in a standard hydrogeological table. For unconfined and semi-confined aquifers, we rely on modified models like Balton, Newman, or the Hantish solution to account for complex factors like delayed yield and leaky aquitards. Next slide. Let's have a sample problem for unsteady flow. Let's apply the Theis equation to a real scenario. Imagine an industrial pump is turned on, and a neighboring farmer is worried about his well located 50 meters away. We need to find the drawdown exactly 1 day after pumping starts. First, we calculate our u parameter using our distance, time, and aquifer properties, which gives us 0.00417. Looking this up in our Theis table gives us a well function, or W of u, of roughly 4.95. By plugging this into our main equation, we find the drawdown at the farmer's well will be exactly 1.57 meters after 24 hours. This proves that groundwater reactions are not instantaneous, the cone of depression expands over time. Next slide. Comparing key well hydraulics equations. To summarize the math we've covered, here is a quick reference guide. Use the Thiem equation for steady flow in a confined aquifer. Use the Dupuit equation for steady flow in an unconfined aquifer, remembering those squared terms. Use the Theis equation for transient, time-dependent flow in a confined aquifer. And finally, use the Hantish-Jacob method for transient flow in a semi-confined, or leaky, aquifer. Next slide. Advanced well scenarios. In the real world, hydrogeologists face advanced scenarios. First, partially penetrating wells. If a well doesn't reach the bottom of the aquifer, it causes 3D vertical head gradients and reduced efficiency, which must be corrected using the Papadopoulos-Cooper method. Second, multiple well systems. When wells are grouped together, their cones of depression overlap. We calculate the total drawdown using the superposition principle, which simply states that total drawdown is the sum of the drawdowns from each individual well. Finally, the method of images. When a well is near a boundary like a river or a solid bedrock wall, we mathematically simulate the boundary by placing imaginary, mirror wells on the map to balance the equations. Next slide. Wells in uniform flow. We must also consider how wells interact with the natural, regional flow of groundwater. Recharge wells add water directly to the subsurface, often used deliberately to counteract severe local drawdown. Pumping wells remove water, which alters the natural flow gradient. To accurately map where a pumping well is capturing its water from, we model the combined flow by superimposing the natural uniform flow with our radial well flow equations. Next slide. Aquifer testing methods. How do we actually find variables like transmissivity and storage for our equations? We conduct field tests. The most common is a pump test. This is a large-scale, controlled experiment where a well is pumped at a constant rate, and the dropping water levels are recorded over time in nearby observation wells. Another method is the slug test. This is a rapid, localized test where a known volume of water, a slug, is suddenly added to or removed from a single well. The rate at which the water level recovers tells us the local hydraulic conductivity directly surrounding the well screen. Next slide. Groundwater pollution and transport. Now that we understand how groundwater moves, we must turn our attention to how it carries pollutants. Understanding contaminant transport is vital for environmental protection. Next slide. Causes of groundwater pollution. Groundwater is highly vulnerable to human activity. Pollutants generally stem from 4 main sources: industrial discharge, such as chemical spills and hazardous waste. Agricultural runoff, from the over-application of fertilizers and pesticides. Waste disposal, specifically leachate from poorly sealed landfills and failing septic systems. And finally, infrastructure leaks, such as corroding underground storage tanks and ruptured pipelines. Next slide. Contaminant transport mechanisms. Once a contaminant enters the water table, it spreads via 3 main mechanisms. First is advection. This is the bulk movement of the contaminant simply being carried along with the flowing groundwater. Second is dispersion. This is the mechanical spreading of the plume caused by water taking different microscopic paths through soil pores. Third is sorption. This is a chemical interaction where contaminant particles physically stick to the soil matrix, slowing them down relative to the water flow. Next slide. Governing transport equations. These mechanisms are modeled using the Advection dispersion equation. It states that the change in concentration, C, over time, T, plus the average velocity, V, times the change in concentration over distance, X, equals the dispersion coefficient, D, times the second derivative of concentration over distance, X, squared. To account for sorption, we use the retardation factor, R. R equals 1 plus the soil bulk density, rho sub B, multiplied by the distribution coefficient, K sub D, all divided by porosity, in. This equation calculates exactly how much the soil will slow down the pollution plume. Next slide. Contaminant transport sample problem. Let's look at a practical example of retardation. Suppose groundwater is flowing toward a river at a velocity of 0.5 meters per day. A chemical solvent leaks into the water. By plugging the soil density, chemical stickiness, the K sub D value, and porosity into our retardation formula, we calculate a retardation factor of 3.13. By dividing our water velocity of 0.5 by our retardation factor of 3.13, we find the contaminant is only moving at 0.16 meters per day. This natural slowing effect is crucial, as it buys environmental engineers valuable time to clean up the spill before it reaches the river. Next slide. Aquifer remediation. When an aquifer is contaminated, we rely on remediation strategies. Pump and treat is the classic approach, extracting polluted water, treating it at the surface, and discharging it. In situ methods treat the water underground without removing it, using introduced bacteria or chemical oxidants. Finally, monitored natural attenuation relies on measuring naturally occurring biological processes to safely break down the contaminants over time. Next slide. Chapter summary. To summarize, mastering steady and transient flow equations is the foundation of well-field design. Aquifer testing provides the physical parameters needed to solve those equations. Understanding advection, dispersion, and sorption allows us to predict the spread of pollution. And finally, engineered remediation strategies, backed by solid hydraulic math, allow us to safeguard our global freshwater resources. And that's it. This concludes our presentation on well hydraulics and groundwater pollution. Thank you for your attention. If you have questions, you write down in the comment section below. If like our content, please like and subscribe to our channel. Maraming salamat po. Mabuhay!